In this video, we're going to be generating qualitative MO diagrams of diatomic molecules. And what we're going to be doing is we're going to combine together different atomic orbitals into molecular orbitals in a qualitative manner. To do this, we're going to be following some simple rules in order to combine together our atomic orbitals and generate our in-phase and out-of-phase combinations. The first rule is that for each atomic orbital used to generate a molecular orbital, we obtain one molecular orbital. So if we mix in two atomic orbitals, we're going to get two molecular orbitals out, and so on and so forth. The second thing is that atomic orbitals must be of the same symmetry to combine to form molecular orbitals. So an orbital has to have the same symmetry label in order for it to combine with another atomic orbital and generate two corresponding molecular orbitals out of that. The third thing is that atomic orbitals must be of similar energy to effectively combine to form a molecular orbital. And remember, what we use for the energy of an atomic orbital is the ionization energy for that atomic orbital. So orbitals that have similar ionization energies are energetically matched and can combine to form molecular orbitals. What we're going to do in this video is we're going to look at the second row diatomics. We're going to look at both homonuclear diatomics and some heteronuclear diatomics. And what we're going to start with is comparing lithium 2 versus beryllium 2. Okay, so we're going to compare the MO diagrams of lithium 2 versus beryllium 2. And the first thing we're going to do is determine which atomic orbitals we're going to use to combine in and mix together. So lithium has a 1s2, 2s1 electronic configuration for the neutral atom, and beryllium has a 1s2, 2s2 electronic configuration. So what we're going to be doing is we're going to be combining together s orbitals. And we're going to start with lithium. We're going to start by drawing our energy diagram where we have energy here, and we're going to put the ionization energies for individual lithium atoms. So here we have a 1s orbital and a 1s orbital. These are going to combine together to form in and out of phase combinations. So our s orbitals are spherical. The in-phase combination looks like this, and the out-of-phase combination looks like that. The lithium 1s orbital is buried significantly lower in energy than the 2s. So to signify this, we're just going to put a hash on our energy diagram, and we're going to continue through with our 2s atomic orbitals, which once again are going to form bonding and anti-bonding combinations. So the 2s orbitals are spherical but larger than the 1s orbitals. They're not as compact. The resulting bonding combination is going to look like that. So it's going to be larger than the bonding combination for the 1s orbital. It's going to be spread out further from the nucleus, and the same with our antibonding combinations. Other than that, from the surface, they're going to look the same. We're now going to go through and we're going to label our resulting molecular orbitals using something more descriptive than the psi1, psi2 notation that we used in the previous video. So this molecule is in d infinity h symmetry, and the resulting molecular orbitals are going to have symmetry labels that reflect this point group. Because of this, this lowest energy bonding orbital is going to have a sigma G label. This will have the one that's anti-bonding, will have a sigma U label. The bonding from the 2s will have a sigma G, and the anti-bonding will have a sigma U. There's a number of different ways that we can further go on to distinguish these. For the purposes of this video, we're going to distinguish our orbitals based on the atomic orbitals that they came from. So our lowest energy sigma G, we're going to give a 1s notation to signify that it came from 1s atomic orbitals. Our sigma U is going to have a 1s. The sigma G from the 2s combinations will have a 2s, and the sigma U will have a 2s to specify. We can further distinguish these by determining what's a bonding and an anti-bonding orbital. If an orbital is an anti-bonding orbital, it's coming from the out-of-phase combinations, then we're just going to put a star next to it. And that's just to help us with our bookkeeping, to help us know that it's an anti-bonding orbital. Last, we're going to start to fill in electrons into these orbitals, starting with the lowest energy orbital and then filling up. So we have 3 electrons from one lithium atom, 3 electrons from another for a total of 6, and we're just going to populate these. 1, 2, 3, 4, 5, 6. And what we've just done is generated the qualitative MO diagram for dilithium. We can go through now and calculate the bond order for this compound. So the bond order, just to remind you, is 1/2 number of bonding electrons minus the number of antibonding electrons. So the bond order is going to be 1/2 of 4 minus 2. So the bond order in this case equals 1. Going forward, we're going to do a few things to simplify this qualitative MO treatment. The main thing that we're going to do is we're going to only focus on the valence orbitals. We're going to treat all of the orbitals that are lower in energy than the valence orbital as core orbitals. The reason for this is that those core orbitals are buried so low in energy that they're not going to participate in any meaningful chemical activity. Instead, they're going to act as an electron screen for the nucleus. Furthermore, the total bond order for all of the combinations for those core orbitals will equal 0. So they're not going to enter into our overall bond order. Going through and just redrawing the lithium 2 MO diagram, focusing on our valence orbitals, we arrive at this. Going through now and drawing beryllium 2, we have to account for the fact that the ionization energy for the 2s orbitals on beryllium are lower in energy than lithium. So when we go through and draw this for beryllium 2, we're going to place the 2s orbitals for beryllium there. These are still going to form our in-phase and our out-of-phase combinations. This is a sigma G formed from the 2s. This is still a sigma U star formed from the 2s, the beryllium molecule. But now, when we fill in our 4 electrons from the beryllium atoms, we get a bond order equal to 0. Based on the bond order, we would predict that beryllium 2 is not a stable molecule. It has a bond order of 0. It has an equal number of electrons described by bonding orbitals and non-bonding orbitals, and therefore will not form a beryllium-beryllium bond. In contrast, we would predict that lithium 2 would be a stable molecule because it has a bond order of 1. These observations have been experimentally verified. For molecules containing other atoms, we have to now consider p orbitals because the p atomic orbitals are going to combine to form molecular orbitals. And we have to consider 2 different orientations in which the p orbitals can combine. So we're just going to consider a generic molecule of the form XX. By definition, when we're talking about the individual atomic orbitals, the z-axis will always be oriented along the bond. So here we can define the atomic z-axis for atom X in this X2 molecule as oriented along that way, and then the X and the Y being perpendicular to that z-axis. Therefore, the pz orbital is oriented like that. In contrast, the px and the py orbitals would be oriented like this, and then coming out of the page like that. The consequence of this is that we're going to form different type of bonds with the pz atomic orbitals versus the px and the py atomic orbitals. Going through and drawing in our energy axis, I'm going to draw our pz orbitals, and this will form an in-phase and an out-of-phase combination. What the in-phase combination will look like is this. And this results from our pz orbitals coming in and overlapping with the 2 in-phase lobes. This gets a sigma orbital designation, and because we're in a nominal d infinity h symmetry, a sigma g label. Another way of thinking about this is that if we have a molecule where electrons are filling this bonding orbital, we can describe this bond just as with the s orbital combinations as a sigma bond. We can also have an out-of-phase combination that we have to worry about. So we're going to form a sigma U star. And it's going to look like that. Taking the px combinations, we're going to form a different type of bond. Because the x, y, and z p orbitals are degenerate, the atomic orbital energies are going to be the same. However, when these two orbitals come in to overlap, they don't overlap as effectively as the pz orbital does in that sigma type fashion. The type of bond that we're going to form is going to be a pi bond. So going through, first off, the symmetry label for this will be a pi u, and for the anti-bonding orbital, it'll be a pi g star. The pi u will look like that, while the pi g will look like that. If we had two electrons occupying the pi u, we had described the type of bond that this would be formed as a pi bond. In general, you have a more favorable orbital overlap with bonds formed in a sigma type fashion than in a pi type fashion. What the consequence of this is that when you form sigma bonds, the bonding orbitals will dive down lower in energy relative to the atomic orbitals than if you form a pi type bond, which won't dive down as dramatically in energy than in the sigma type case. We're now going to go through and generate molecular orbital diagrams for F2 versus diboron. So starting off, generating our energy axis. We have this, and we're going to start with the F2 molecule. So we have two fluorines. We'll put in our 2p orbitals. And our 2s orbitals. We're going to overlap our 2s orbitals. Generating in and out of phase combinations. Then going to overlap the 2pz, generating that sigma interaction. And then finally the 2px and 2py generating our pi type orbitals. Going through and filling in our electrons. We arrive at this molecular orbital diagram. Going over and now doing this for diboron, we're going to change the energy of our 2p's and our 2s's to reflect the fact that the ionization energy for the 2p and the 2s electrons in boron are much higher than they are for fluorine. So here, we have our 2p's here, and then we're going to put down our 2s's here. And when we go through and generate our molecular orbital diagram, it's going to look something like this. and filling in those electrons, we have this. Now, if you look, you might notice that there is a difference between the difluorine compound and the diboron compound. And that is the ordering of the orbitals that result from the 2p combinations. In the case of difluorine, we have the sigma G, lower in energy than the pi U orbitals. In the case of the diboron compound, we have the opposite. We have these pi U's that are lower than the sigma G orbitals from the 2p's. The reason for this has to do with something called orbital mixing. Remember, in order for orbitals to overlap with one another, they have to have the same symmetry and they also have to have similar energies. Now, the energy axis that I drew on this molecular orbital diagram really doesn't do justice with how deeply buried these fluorine 2s orbitals really are. So what I'm going to write here are the ionization energies for the 2p and the 2s orbitals for fluorine versus boron in terms of electron volts. And 1 electron volt is equal to 23 kcals per mole, which is equal to 81,000 wave numbers for reference. In the case of fluorine, the 2p electrons have ionization energies of 18.7 electron volts. For boron, those are about 10 eV higher, so those are 8.30 eV. Now, because those p electrons are poor at shielding the nucleus, the 2s ionization energy for fluorine is very low. It's 46.4 electron volts. And we can compare this with the 2s electron ionization energies for boron, which are 14.0 eV. As we can see, there's a significantly closer energy match between the 2s and the 2p's in boron than there is in fluorine. Because of this, we can get mixing between the sigma type orbitals in boron that you just do not observe with fluorine. So we can get additional interactions like this, that's going to raise the energy of that sigma G orbital formed primarily from the 2p overlap, so that it's higher in energy than the pi U's. What I'm going to do is I'm going to look at the formation of the sigma G and the sigma U orbitals from the 2s and the 2p orbitals in the absence of the other p orbitals for better clarity. And we're going to do this with and without orbital mixing. So on the left, we're going to have without mixing, and then on the right, we're going to have with mixing. Put in our 2p orbitals, then our 2p orbitals, our 2s orbitals, and now we're going to overlap our 2s and our 2p orbitals. Now, when we go through and turn on mixing, it's going to primarily influence the energy of these two orbitals right here, the sigma U star from the 2s and the sigma G from the 2p. So going through and doing this, You form your sigma G from the 2s. The sigma U star from the 2s, which now has a little bit of 2p character. The sigma G from the 2p, which now has a little bit of 2s character. And then the sigma U star from the 2p. For your homonuclear diatomics, where you're going to see this break on the second row of the periodic table is at the nitrogen-oxygen divide. Up to nitrogen, you're going to see mixing, and then once you get past nitrogen with oxygen and fluorine, mixing is turned off because those 2s orbitals just go way too low in energy to effectively mix in to raise the energy of that sigma G from the 2p combinations. We're going to end this video by talking about heteronuclear diatomics. So recall that we can make a molecular orbital as a linear combination of atomic orbitals that have been weighted with various coefficients in front of them. For a homonuclear diatomic, we are making molecular orbital diagrams primarily from combinations of two atomic orbitals. So C1, Phi1 plus or minus C2, Phi2. In this case, C1 equaled C2, and the reason for this was because the energy of our atomic orbitals were identical when we were combining these together. Therefore, you had equal weights of each atomic orbital into the overall molecular orbital. When we go to these heteronuclear compounds, this is no longer going to be the case. So in the case of heteronuclear diatomics, if we take two atomic orbitals to combine together to form a molecular orbital, we're going to have this once again. However, C1 is not going to equal C2. So you're going to get more of one atomic orbital character in that molecular orbital than you are of the other. And this is simply because the energies of our atomic orbitals are no longer equal to one another. What I'm going to do now is introduce a new rule for the formation of these qualitative MO diagrams. And this new rule is that the molecular orbital will more resemble the atomic orbital that is closest in energy to. And what I'm going to do is I'm going to generate molecular orbital diagrams for HF and CO to emphasize this. I'm now going to go through and draw the qualitative molecular orbital diagram for HF. And before we do this, we have to know a little bit about the ionization energies of the atomic orbitals that we're dealing with. As we've previously said, the fluorine 2s has an ionization energy of 46.4 eV, and the 2p has an ionization energy of 18.7 eV. Hydrogen has a 1s orbital that has an ionization energy of 13.6 eV. So going through, we're going to draw this out. Here, we're going to put hydrogen over here and fluorine over here. We have our fluorine 2p orbitals, and then buried down significantly lower in energy is the 2s orbital. Up here, we have the hydrogen 1s orbital. Going through and combining these, it's the 2pz orbital on fluorine that has the appropriate symmetry to overlap with the hydrogen 1s orbital. I'll be drawing this out in a second. So we're going to form a bonding and an anti-bonding pair with that. The 2s orbital on fluorine is so low in energy that it's not going to participate in bonding to that hydrogen 1s orbital. So it's going to come across as a non-bonding orbital. The same thing is going to apply for the 2px and the 2py orbitals. So your 2px and y are also going to be non-bonding orbitals. So I'm going to draw what these molecular orbitals will look like over to the right here, with the hydrogen facing this way and the fluorine facing this way. Okay. In addition, I'm going to turn this into a Lewis structure. So I'm going to put in 3 lone pairs on fluorine. Drawing this out, this lowest energy orbital is going to be almost exclusively fluorine in character. So it's going to have no contribution from the hydrogen. So that this doesn't look like simply an isolated s orbital, I'm just going to draw a line with a dot just to signify that the hydrogen nucleus is there, but there's no orbital density associated with that hydrogen nucleus. This non-bonding orbital has sigma-type symmetry. Because we're no longer in d infinity h, we're in c infinity v. We're going to drop the g and the u symmetry labels because we've lost the inversion center in the molecule. And we're just going to label this as a sigma 1 2s. The other 2 non-bonding orbitals originate from the 2px and the 2py. So I'm just going to draw those out. There's one of them, and then the other. Trying to draw this 90 degrees rotated from that, so it's really coming out of the screen towards you. That's just to try to give it some depth. These have pi-type symmetry, so we're going to call these our pi 1 2p's. This bonding combination from the hydrogen and the fluorine, it's closest in energy to the 2pz orbital and further away from this hydrogen 1s. Because of that, it's going to have more fluorine 2pz character to it than hydrogen 1s. So what this orbital is going to look like is it's going to look something like this. And that's resulting from the hydrogen 1s overlapping with the fluorine 2pz. This also has sigma-type symmetry, so we're going to call this a sigma 2, and we're just going to call it HF to specify that it's coming from both the hydrogen and the fluorine. This HF is just an arbitrary label that we gave it to keep the accounting in mind in our head. The antibonding combination is going to be looking like that. However, this is now going to be dominated by the hydrogen 1s because it's closest in energy to that. So what this is going to look like is something like that. Okay, so that's what the sigma 3 star from the HF is going to look like. Going through, filling in our electrons, we have 8 valence electrons we have to deal with. So we're going to be putting that here, 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 and here. Now there's a few predictions that we can make from this molecular orbital diagram that make sense with things that we've learned from classes like general chemistry. The first thing is that this MO diagram makes some sense with the Lewis structure of HF. The Lewis structure of HF, we would predict there to be an electron pair bond between the hydrogen and the fluorine, and then 3 lone pairs surrounding the fluorine atom. And that's exactly what we see. We see this sigma bond, which corresponds to our electron pair bond. And we also have non-bonding orbitals that are almost exclusively isolated on that fluorine atom. So we have this sigma 1 orbital, and we have these pi 1 orbitals that you can think about as being these lone pairs on that fluorine. The second thing that makes sense is that we would predict, based on electronegativity, that there would be a large partial positive charge on the hydrogen, and there would be a large partial negative charge on the fluorine. And this also makes sense. If we look at the molecular orbitals that have electrons associated with them that we generated, those are all fluorine-dominated molecular orbitals. Therefore, all of the electron density is going to be distributed onto that fluorine atom. In contrast, the hydrogen-dominated molecular orbital is an unfilled orbital. So therefore, we would predict that hydrogen would not have a large negative charge associated with it. In fact, it would have a partial positive charge associated with it, just because the electron density is not associated with the hydrogen atom in this molecule. We're going to finish this by looking at the molecular orbital diagram of CO. So starting just like we did with HF, we're going to look at the ionization energies for the 2s orbitals and 2p orbitals associated with carbon and oxygen. So for carbon, it's 19.5 eV for the 2s, 10.7 EV for the 2p. For oxygen, the 2s has an ionization energy of 32.3 eV, and the 2p has an ionization energy of 15.9 eV. We're going to go through and just draw this out. I'm going to put carbon here and oxygen over here, and have the carbon 2p orbitals here, and the 2s orbital here, the oxygen 2p orbitals here, and then much lower in energy, we're going to have the 2s there. And I'm going to bring this over and essentially call this a non-bonding orbital for the oxygen 2s. So what we're left with are overlapping these orbitals here. And what's going to happen is this 2s orbital is going to be able to provide for orbital mixing as we go through and generate this, because it has a nice energy match with the 2p's here and the 2p's here. So I'm going to go through and start just by mixing in the pi type orbitals. Now we're going to go through and mix in the sigma interaction between the PZ on the oxygen and the S on the carbon. We have another PZ sigma type interaction like that. And then this is going to go up in energy here. So what we have is our sigma 1, our sigma 2, pi 1, sigma 3, pi 2, and our sigma 4, going through and placing electrons in. We have this. I'm now going to do two things. The first thing I'm going to do is draw out the Lewis structure of this molecule here. And I'm also going to add in what these molecular orbitals look like, but instead of drawing them out, I'm going to put down plots that are the results from electronic structure calculations that went through and calculated the molecular orbitals for the CO molecule. So these are the computer-generated plots for the MOs for the CO molecule, with the two different colors signifying the two different phases of the molecular orbital. And we're going to go through and do a few things in order to correlate some observable properties of CO with its molecular orbital diagram and also relate back to the Lewis structure. So if we look at the Lewis structure, what we have is a triple bond. We have a lone pair on oxygen and a lone pair on carbon. Now the three bonds making up that triple bond correspond to sigma 2. So there's your sigma bond. And then the two degenerate orbitals of pi 1. So there's your pi bonds. Okay. Your lone pairs are sigma 1, so there's your oxygen lone pair, and sigma 3. So there's the carbon lone pair. And as you can see, these are not exactly perfect analogies. So with that sigma 3, there's a significant amount of oxygen character in that molecular orbital. However, it's dominated by the carbon. So we can call it a carbon lone pair to a first approximation. And this is going to give us some insight into a little bit of the chemistry displayed by CO. So we know that CO binds to a metal center through the carbon. The reason for this has to do with the frontier molecular orbitals of CO. So specifically, the highest occupied molecular orbital, the HOMO, which is our sigma 3 orbital, and the lowest unoccupied molecular orbital, or molecular orbitals in this case, the degenerate pi 2 orbitals. As we'll see, a lot of chemistry can be rationalized using a frontier molecular orbital analysis, understanding how the HOMO and the LUMO of molecules interact with one another. For CO, the reason that it binds through the carbon is that the HOMO, the electron pair that it can donate into the metal center, is mostly carbon-centered, while the LUMO, the orbitals that can accept electron density from the metal center, are also mostly carbon-dominated. And this is why we get primarily binding of CO to a metal through the carbon as opposed to its oxygen. So that ends our qualitative analysis of diatomic molecules. In the upcoming video, we're going to look at MO analyses of polyatomic molecules.